Oke dah. Dengar tak?
Quick overview of the Beer-Lambert law and how we use it in the chemistry lab.
Dengar.
Yes, the Beer-Lambert law has absolutely nothing to do with beer. It's actually named for these two guys, Beer and Lambert. We're the first to recognize that the absorbance of light is related to the concentration of whatever they were looking at. This is a very powerful technique for the analysis of samples in the chem lab, and it's something we'll be using fairly frequently during the semester. Whenever you're in lab, it's not uncommon to run into solutions that we know the concentration of. In this example, here are 5 cobalt solutions that vary in concentration from 0.1 molarity to 0.5 molarity. The reason we chose cobalt for this example is cobalt is red in solution. So hopefully you can see that as my concentration increases from left to right, the depth of the red color also increases correspondingly. So low concentration, not much red color; high concentration, a deep red. It is not uncommon to run into solutions in lab that I don't know the concentration of. So for example, here on the right, solution of that same cobalt that I don't know its molarity. I can estimate the concentration of that unknown based on the color of red in that solution. And if I look carefully, I can see that red color over here on the right is darker than the 0.3, but it's definitely lighter than the 0.4. So that molarity is going to fall in between those two solutions. Maybe I would estimate 0.35. Sometimes an estimate is good enough. However, there are many times we need some more accuracy. And to get that accuracy, we're going to use an instrument called a spectrophotometer. A spectrophotometer is an instrument that can pass light through solution. When we do this, we know how much light is being sent in to the solution, and we measure how much comes out. And there's always going to be a difference in those two readings. In this figure, you can see I'm passing quite a bit of red light into the solution. Some of that light is getting absorbed by the solution. So when it gets done traveling through it, less light comes out. What Beer-Lambert did was they put some mathematics to this relationship. And the Beer-Lambert law is given by this equation. The absorbance at a given wavelength or color of light, which I'll get into in a second, is related to 3 terms. A constant E, which is a constant for whatever chemical we're looking at, the path length, and the concentration. The path length and concentration are important because the path length is the amount of distance the light passes through the solution. So the path length in our example is very short, it's just how much the width of the container. But these can be very narrow or very wide, so that's going to change something. And the concentration, which here I show in molarity because chemists work in molarity very commonly, but the truth is, Beer's law, or Beer-Lambert law, works for any concentration unit as long as you're in. Thankfully, we don't need to work with this Beer-Lambert law in this form. We usually look at it in a slightly different way. The way that chemists work with Beer-Lambert law is we go back to those 5 solutions that I know the concentration of. So here you can see I've got my 0.1 to 0.5 molarity solution. I'm going to put those into my spectrometer and I'm actually going to measure the absorbance. If you look now, I've got this extra term in here that says absorbance at 472 nanometers. This 472 nanometers lets whoever looks at my data know what wavelength of light I'm passing through the solution. The way to think about this is actually color. 472 nanometers falls in the visible range, and it's actually some green light. So I'm passing green light through these red solutions. What I hope you notice is that as my concentration increases, my absorbance also increases. So as I get more stuff in there, more of that light's being absorbed. Once I have this data, I use it to create a Beer's law plot. A Beer's law plot is just absorbance plotted against concentration. So I've got absorbance on my y-axis, concentration on my x. Once I plot my points, it's very common to fit a trend line. So here's the equation for that trend line, and an r-squared value to that number. Once I have this plot, I can use it to figure out the concentration of my unknown. The way I do that is I take that same unknown solution, I put it in a spectrometer, and I measure its absorbance at exactly the same wavelength, at 472 nanometers with that green light. When I did this for this example, it comes out to 0.47. If we look back at the original data for our 5 known molarity solutions, it falls between the 0.3 molarity and 0.4 molarity solutions, which should make sense. That's where we estimated it way back when we were just looking in color. So that's a good thing. We can also look at it here on the plot. We can find the absorbance on the y-axis, and that's where it lives. So 0.47 is about where that black arrow is. We can draw a horizontal line to where it intersects with that trend line, and we can drop it down to the x-axis, which is my concentration. And eyeballing that, we got a molarity of about 0.35. Again, that's as good as our eyeball with just the colors. We can do even better with a little bit of mathematics. The mathematics comes from this trend line equation. If we look at that equation from the plot, again, I just pulled it off of there, we need to recognize what each of the variables are. In this case, y is my absorbance value, and x is my concentration value in terms of molarity. For our unknown solution, we know the absorbance. So to figure out concentration, all I need to do is plug that in for my y and solve for my x. So here on the right, I do show the mathematics. I set it equal to 0.47, and I isolate for my x term. So move everything around, get the x by itself. I get a 0.34 molarity solution, which is really close to my estimate. But this is a much more accurate way to get that concentration. Beer's law is pretty easy to work with, but there is one major consideration that we always need to pay attention to when working. When working with Beer's law, again, we're going to have some standards. Again, those are known molarity solutions, and we can measure concentrations of unknowns. So in this example, I measured an unknown there. I could drop it down, figure out its concentration, or if I have the trend line equation, I could do the math. The problem arises when I get unknowns that have absorbances that don't fall between the standards. So that one's going to fall way up there. We'd like to think that if we did the mathematics, it would still give us good data. But the truth is, Beer's law is only linear or straight line for short distances, and we can only trust it between our standard points. The take-home message from this, if you're measuring the absorbance of an unknown, it must fall in between the standards. So in this case, where my mouse is indicating between standard 1 and standard 4, that's where all of our unknowns have to fall. If they're outside of that range, we need to do some adjustment. If it doesn't fall in the range of our standards, one fix is to add more points to the line. Make a more concentrated or more dilute standard just to get it on the line. The other way to do it, and is more common, is you take and you dilute your unknown sample. So maybe unknown 2 is way too concentrated. I can cut it 50-50 with water. That may pull it down somewhere in between my standard points, which will give me good results. The problem with this is then it does take one more math step to get back to the original molarity of the unknown. Now, this has been a very quick introduction. We're going to cover this a little bit more in lab, coming up very soon. If you have any questions, please ask them during that time.
Okey, lepas tu kita nak buat apa? Kita buat table dulu kan?
Nombor 2. Nombor 1 tu saya buat kan sebenarnya.
Kat mana tu?
Ataupun tengok dekat media interface tu.
Ini kan.
Yang ni lah.
Kita dah buat table, isi.
And then yang ni nombor 2. And lepas tu graph.
Okey, ni graf. Allah. Ni slide kan. Yang betul-betul tadi yang kita buat. Betul?
Bukan.
Ni.
Yang 7.0 kat yang ni.
Kita orang akan dapat 7.0.
And then jalan kerja.
Jalan kerja kita orang buat macam ni. Y sama dengan MX tambah.
So dapat 6.99 sama dengan 7.0 lah. Lebih kurang.
6.99 tu sama dengan 7.0 je lah kan?
Sama tu.
Okay, right. Ini je kan kita kena buat.
Tu je kan?
Lepas tu sekejap aku tunjuk. Lepas tu kita masukkan dalam box kita tu. Sekejap Sekarang ni aku kena share screen ke macam mana?
Box yang mana? Yang
yang ni.
Ni bawah.
Yang ni okey je lah. Tunjuk yang ni je lah. Okay, so ni adalah result kita.
dah siap.
6.9 sama dengan 7.0.
I end recording
Thank you
Okay.
for the kita sama yang diberi. Sekejap nak tanya.
Okay.
Dalam box tu kan, untuk result kita tu,
Ni.
concentration of yang last tu unknown kita tu kan 6.99 tu kita tak payah bunda ke jadi 7.00 sebab kan kat graf kita 7.7.
Bunda kan je lah. 7.0.
Tukar je lah kan. Jadi
boleh je.
okey.
Dah tu
Jika
je.
korang nak buat lab report korang buat macam ni lah. Tapi yang tu tukar jadi 7.
So I stop recording.
Okey.